So now let's finish our exercise. How to approximate. So in order to approximate the value of the integral, now we need to approximate the sum of the series. Now, the main observation for this series is that it is an alternating series and it's convergent according to Leibniz test. Yes, you know the Leibniz test says the following: you have a series of this type, and if an is decreasing to 0, then the series is convergent. This happens here, obviously, but moreover, for an alternating series, we have the following result to approximate the sum of the series. It says the following: if we denote the S by S, the sum of the series, and if we replace it by the sum from 0 to n, yes, so we add up to an arbitrary n, then the error we are making in this way will be less than an plus 1. So the error is less than the first neglected term, because an plus 1 is the first term that we do not sum. Yes, we stop at an, and an plus 1 is the first neglected term. Okay, so this is the result about the approximation of alternating series. Okay, so let's see how we apply it. It's very simple. We just need the list n, who is the list n, which satisfies the condition module of, in our case, 1 over 2n plus 1 factorial times 2n times 4 at n, actually, so this one is 4 at n, must be less than the given error. Yes, and the list n will be the first neglected rank. Yes, in our case it's 10 minus 3. That is equivalent with 2n plus 1 factorial times 2n times 4 at n greater than 1000. And now we find the list n satisfying this inequality, and that will be the first neglected term, the rank of the first neglected term. If we put here n equals 2, what happens? Here we have 120 times 4 times 16, which is obviously greater than 1000. So actually, n equals 2 is already the first neglected term. So we need to add up to 1. That means the first term in this case. So the value, the approximate value, will be only if you take the first term, which is it's an exceptional case. Usually this is not true, but in this case it holds. So it is 1 over n equals 1. You get 6 times 2 times 4. So it's 1 over 48. So 1 over 48, it's an approximation of this integral, and the error we are making in this way will be less than 10 at minus 3. If we want to improve the error, we want, for instance, 10 at minus 4, we must, of course, usually increase n, of course. The less the error, the greater is n, of course. We must add more and more terms. Okay. If you have any question about this kind of exercise. And here, the usual functions, the usual elementary functions can appear in exercises, yes? Such as square roots, logarithms, exponential, trigonometric function, inverse trigonometric functions. Yes, you must know their power series and used in this way. if you have any question. Okay, so let's see another type. For example, to compute the sum of a power series and to find its sum. Here, the basic result is about the sum of the geometric series. So we must know that sum of Q at n starting with 0 equals 1 over 1 minus Q. Attention, if and only if modulo of Q is strictly less than 1. This is an elementary result about the geometric series. This is the kind of result, theoretical result we need. Let's take, for example, a power series. Let's consider this one. N, let's put it here, 2, n times x at, let's say, n minus 1. So consider this power series, and the questions are: compute the radius of convergence, find the domain of convergence, and compute the sum of the series, the function s of x, which is the sum of this power series. Now, the technique, it's straightforward. For the radius of convergence, we have a formula. Actually, we have two formulas. We apply which one is more appropriate. The usual one is this one. If we have this power series, the radius of convergence is modulo of an over an plus 1, the limit of this, which, if in some cases, in most cases, equals this one. Sorry, 1 over. This is an elementary result. But usually, the usual way to compute it is to compute this limit, which in most cases is simpler. Okay. So if we do this in our case, tell me what's the radius of convergence of this power series. I am waiting to your answer. Of course, it's 1. So the radius of convergence is 1. Now, what's the theoretical result from here? What does it result from here about the convergence of the series? It says the following: if modulo, it is x centered at 0, so if modulo of x is less than 1, then our series is absolutely convergent. If modulo of x is strictly greater than 1, it is divergent. So this is the theoretical result called the radius of convergence. On the interval, on the open interval minus 1, 1, if we fix an x here, we shall get here an absolutely convergent series of numbers. In order to find the domain of convergence, we need to check what happens at the end of the intervals, because the theory says nothing about the ends of the interval. So when x equals minus 1, we get a series sum n times minus 1 at n minus 1, which is convergent or divergent.
Divergent.
It is divergent. Give me a reason. Why do you think it's divergent?
Because
Because, no, tell me a test. Because of the necessary test. The necessary test says if this one doesn't tend to 0, and it doesn't, then the series is divergent. Very well. When x equals 1, we get sum of n, which is obviously divergent because of the necessary test. So finally, we found the domain of convergence. It is the open interval minus 1, 1. Yes. So the sum of the series S is defined on this interval, minus 1, 1, taking values in R. And now we have to compute it. Okay. What are the tools here in order to do that? The tools are integration term by term or differentiation term by term. In other words, think what should we do to this series in order to get a geometric series. So the idea is to somehow use at some moment this result about geometric series.
We can integrate.
We need to integrate because we observed n times x at minus 1 is actually the derivative of who?
Of x at power n.
Oh, a second, this is obviously. And now, because of a property of power series, which says that power series can be differentiated term by term, we did prove this at the lecture, we have this. Yes? So S of x is the derivative of this sum. But the sum inside, it's a geometric series, yes? This is the derivative of who? Who is the sum of this series? Attention, it's here, x at n, of course, here. Attention, it starts with what power of x?
X squared.
So this is x squared plus x at 3 plus and so on. Attention, the general result, I mean this one, the sum is this one because it starts with 1. Yes, 1 plus q squared and so on equals 1 over 1 minus q if modulo of q is less than 1. So here we have, you can do in two ways. You can add and subtract the first two terms or take off x squared. Is the same. So this is, if you want, x squared times 1 plus x at 2 and so on, differentiated, which means x, which is x squared times what? 1 over 1 minus x, derivated. Yes, so the sum of our series equals the derivative of this function. Yes. And now we simply differentiate here and we get a sum. Yes. This is 2x times 1 minus x. Below we have 1 minus x squared. Minus, actually plus x squared, yes. So it will be 3x squared. No, sorry. We have 2x minus x squared over 1 minus x squared. Okay, this is it. This is the sum of the series. Actually, what we did here was to integrate that. Here we observe that this is the derivative directly and yes. Okay. Other ideas is to differentiate. For example, if let's consider the following power series, sum of n greater or equal than 2, let's say, of say -1 at n times x at n over, let's say n plus 1. Let's put it like this. Well, please first compute the radius of convergence. What's the radius of convergence? Let's write it exactly as a power series, as we are used to write a power series like this. X at n. Okay. So, who is the radius of convergence here? Please compute it and tell me the result.
1.
So the radius of convergence is 1. So what the result says, on the open interval -1, 1, it is absolutely convergent. Outside it is divergent. We don't know what happens at -1 and 1. We need to compute. So when x equals -1, we get the series sum of n greater or equal than 1, that -1 at n times -1 at n over n plus 1. Tell me the nature of this series of numbers.
Divergent.
It is divergent because it is the harmonic series. This is 1. Very well. When x equals 1, we get what? Which is?
Convergent.
Is convergent because this is the harmonic series. Yes, the harmonic series. Or you can prove the convergence by using Leibniz test. It's an alternating series. Okay. So now the domain of convergence is the following. -1 open, 1 closed. So the function S, which is the sum, will be defined here. So the sum of this series, it's a function defined on this interval. Open at -1, closed at 1. And now how to compute the sum? Well, here it's clear that here it was an integration sum. We need to derivate this because we need to simplify n plus 1 from here. But if we differentiate it like this, the derivative of x at 1, x at n will be n times x at -1, and this n will not simplify with n plus 1 from below. What can we do?
Can multiply and divide by x.
Very well. So if we write a sum like this, it starts with 2, yes? Let's write like this, -1 at n over n plus 1. We need here x at n plus 1. And for that, we need to divide by 1 over x, which can stay outside the series because it is constant with respect to n. Okay. And now, instead to compute this sum, we'll compute its derivative, yes, s prime of x, because this is s of x, written in this form. It will be -1 over x squared times the sum. We differentiate as a product, yes? Plus 1 over x, and the derivative of this 1. Okay, let's start with a simpler exercise first of all. Okay, I shall come back to this one, but let's make it in two different exercises. Let's start with this one. Okay, let's start with this one, and then we shall do the other one. Not move directly to the most difficult. let's start with this one. Of course, the radius of convergence is 1, is the same. The domain of convergence is -1 open, 1 closed, is the same actually. I changed a little bit. And now let's compute the sum of the series, which is defined on this interval. So the idea is to get a geometric series, yes. So let's compute the derivative of s prime of x equals this one, derivative. Now we use the property that power series can be derivated term by term, so we get nx at n minus 1, yes. We simplify by n, and we get the following geometric series actually. If you want to write few terms, when n equals 2, we get x. Then when n equals, it's minus x at 2. Yes, for n equals 3. N equals 2 was the first, we get x. Then for n equals 3, we get minus x. Then when x equals 4, we get plus x at 3, and so on. What's the sum of this obviously geometric series? It is a geometric series with the first, you can write it x times 1 minus x plus x squared, and so on. Okay. So it gives x times, this is the geometric series with ratio, what is the ratio here?
Minus x.
Here. Minus x. So the sum will be 1 over 1 plus x. So it is x over 1 plus x. This is the derivative of the function s. S of x, derivative, it's x over 1 plus x. And now we need to compute s of x by integrating. So s of x will be one of the primitives of this function, which is integral of 1 minus 1 over 1 plus x. If we make the division of the polynomials, okay, which gives us x negative logarithm of 1 plus x plus a constant. How to find this constant? Simply by trying to compute s of 0 directly from the definition. If we look to the definition of s of x, here, sorry, this one, yes. You see here the first term is x squared. So obviously at 0 it will vanish. So s of 0 is 0. Yeah. So on one hand, from the power series s of 0 is 0, and from here s of 0 it still is the constant. So the constant will be 0. So finally the function s will be x negative logarithm of 1 plus x. Okay. And now if we go back to the first exercise, but I think for the partial exam this is enough. Here you need to simplify by x, yes, to divide by x. Yes, remember, because here the function was our function divided by x. So it's clear what happens. Plus one term, maybe it's here. It's the first term maybe is missing. So if you divide this one by x, you get the function, the initial function, and you can see at 0 it still vanished because you get 1 minus logarithm of 1 plus x over x, and when x tends to 0, this tends to what? logarithm of 1 plus f over x. When x tends to 0, this one tends to 1. So at 0, you get 1 minus 1, which is 0. So it's okay. But I shall not go so far. I will stop to direct operations for the partial exam. Differentiation and integration. And you have examples from both. So the geometric series is the basic tool. Of course, you must know to compute the radius of convergence, which is rather simple. And of course, to integrate or differentiate term by term, but it will be directly. I mean, not other transformations, because the goal is to apply the basic theory. Now, what else? Well, Taylor polynomials. First, and linear and quadratic approximations for functions of one single variable. Here you must know the formula, and of course you must know how to compute derivatives. So actually this is a college exercise, but it's useful to remember, to see that you can, you know how to compute the differentials. For example, let's take f of x equals x squared times square root of, no, not here. Let's say 2x plus 1 times x squared plus 1 at x equals 0. So let's write the Taylor polynomials at x equals 0 for this function. Okay, so Taylor polynomial, the first degree equals f of 0 plus 1 over 1 factorial f prime of 0 times x. This is f t1 and t2 of x. It's the previous plus the next term, it's f second of 0 over 2 factorial times x squared. Actually, if we compute t2 is directly. So what we need to compute, it's f of 0, f prime of 0, and the second derivative at 0. So f of 0 equals 1. Don't forget the function, it is this one. F prime. Now let's compute f prime of x. Here, attention, you need to compute it properly. Don't make mistakes when you differentiate something, because calculus means, first of all, to compute derivatives and integrals. So don't make mistakes when you compute such things, because these are the most important, actually. So the derivative is 2 times x squared plus 1 plus 2x plus 1 times here we get 2x over 2 square root of x plus 1. You simplify by 2 and you get 2 square root of x plus 1 plus, here you get 2x squared plus x over root of x squared plus 1. Let's do it again. Every derivative must be computed twice at least. So the function, it is this one. 2 times, okay, plus 2x plus 1 times 2x over 2 root of 4x. Okay, so it is this one plus, here we simplify by 2 and we get 2x squared plus x over, okay. So f prime of 0, it is 2. And now the second derivative. In this moment, one can write the Taylor polynomial of the first degree, but we shall compute also the second derivative. So we need to differentiate this function and to compute this value at 0. So it is 2 times 2x over 2 root of x squared plus 1. Of course, here we simplify. Plus 2. Sorry. This was the derivative of this term. Now plus the derivative of this ratio. You can do it in two ways, as a ratio or as a product, if you prefer to compute this one as a power. Okay, let's do it as a ratio, as it is written here. So the denominator is x squared plus 1, and above we have 4x plus 1 times root of x squared plus 1 minus 2 squared plus x times 1 over 2 root of x squared plus 1 times 2x. Now, of course, we can continue to simplify the expression. In some exercise, we need it, but here is not the case, because we need to compute f second at 0. F second at 0. This one is 0, plus here, this, of course, this ratio normally should be simplified. But in this case, it's not necessary, because you see, the second part here will be 0 if you put x equals 0. So the only remaining, it is this one. If you put here x equals 0, you get 1, you get 1. So this will be 1. So now the Taylor polynomials will be T1 of x equals f of 0, that is 1, plus f prime of 0 is 2. So 2 over 1 factorial is 1 times x, and T2 of x will be 1 plus 2x plus 1 over 2 factorial, so that is 1 over 2, times f second of 0, which is 1, times x squared. So these are the Taylor polynomials, which approximate the values of the function f close to 0, around 0. Okay. If you have questions, please. Some particular questions, some.
I have a question, but it's not about the Taylor polynomials.
Okay, not necessarily. Okay.
If it's not too late and we have some time, I would like to discuss a little bit about countable and uncountable sets.
Okay.
And if you can show us an example of a demonstration that a set is not countable.
Okay. In the lecture, you have two such proofs. One of them is the classical Cantor's diagonal argument. So for example, you have the following example, and you may have the partial small variations around the same idea. So Cantor's diagonal argument is the following. The set. Okay, I shall change the blackboard. Yeah. Yes, of course we can discuss. We can discuss everything which is related to our partial. So let's consider the set X, the set of all strings of this form, where AG belongs to a set with two symbols. Call them 0 and 1. This is how I put in the lecture, but we can change. Doesn't matter here. 0 and 1 are not necessarily the number 0. Well, this set is uncountable. Okay, what's the idea of the proof? Is to suppose by contradiction that X is countable. And finally, to get a contradiction with a hypothesis. Okay. What it means for a set to be countable? It means that it is in a one-to-one correspondence with a set of natural numbers. Moreover, what that means? It means that we can write its elements, yes, as a sequence. You are the first, you are the second, you are the third, and so on. That is the one-to-one correspondence with a set of natural numbers, 1, 2, 3, 4. So That means X can be written as a sequence, X1, X2, X3, and so on. And obviously, this is the one-to-one correspondence with the set of natural numbers. This one corresponds to 1, this one to 2, this one to 3, and so on. This is the one-to-one correspondence. So again, if X is countable, it means it can be written, its elements can be written as a sequence. But attention, the supposition is that here we wrote all the elements of X. Nobody is missing. So the set X equals. Now, who is X1? X1 must be an element of X. Who are the element of X? They are sequences of 0 and 1. So here I need to write a sequence of 0 and 1. I shall use two indexes. Not okay. For instance, I shall put below the fact that this is a symbol in X1 and its position is the first position. The position will be up above. For example, not necessary. The second symbol in X1 will be A1 because it belongs to X1, and I shall put here 2, A1, 3, and so on. Attention, who are these elements? A1, 1, A1, 2, A1, 3, and so on. They are 0 or 1, each of them. So it's something very simple. Now, X2, the second element here. It's a sequence of 0 and 1. I shall put the index below because it belongs to X2. X2, 1, X2, A2, 2, A2, 3, and so on. X3. It's a sequence of 0 and 1. A3 because it belongs to X3, 1, in the first position. A3, 2 because it belongs to X3 and it is the second position. A3, 3, and so on, X4, and so on. And now the contradiction will be obtained in the following way. If we are able to find an element Y, which belongs to X, so it's a sequence of 0, 1, about which we can prove that it cannot be X1, it cannot be X2, and so on. So it doesn't appear in this sequence here. It cannot be none of them. Who must be Y? Well, this is Cantor's diagonal argument. It's a sequence of 0 and 1. It is B1, B2, B3, and so on. Bj must be 0 or 1. Attention here, Aij, Aij, it's 0 or 1. All these symbols here in this table are nothing but 0 or 1. Okay. Now the question is this one, how to choose B1? And this is what is called Cantor's diagonal argument. How to choose B1? In this element about we would like to prove that it cannot be X1, it cannot be X2, and so on. Well, we will choose B1 to be different from A11, from this one. Now the question is it possible? Yes, it's possible because A11, it's 0 or 1. If it is 0, I take B1 to be 1. If A11 is 1, I will take B1 to be 0, so it's possible. How to choose B2? Now, please tell me. You got the idea, I'm sure.
A22 is on the diagonal, so it's going to be A22.
So it must be different from A22, yes, from this one. Is it possible? Yes, of course, because A22 is 0 or 1, and B2 will be the other one, and so on. So B3 will be different from A33, and so on. And now the question is why the element Y written here, it cannot be one of the elements written here in this sequence. Well, it cannot be X1. Why? Because Y and X1 are different where? At what position?
B1.
on the first
At the
position.
first position.
Exactly. Y on the first position has B1, and X1 on the first position has A11, and they are different. Y is different from X2, simply because on the second position, here, Y has B2, and X2 has A22, and they are different because of this choice, and so on. So Y cannot be one of the elements written here because it cannot be X1, it cannot be X2, and so on. For example, Y cannot be, let's say, X1987. Why? If somebody tells you, look, your argument is wrong, I tell you, the 1987th element from this sequence will be equal to your Y, to your element Y here, so you did nothing. What's the argument? Why they are not equal? Simply because on the 1987th position, they are different. Yes, because B 1987 is different from A 1987, 1897. Okay, so this is it. So here in this sequence, we don't have all the elements of X. At least this one is missing. So contradiction. So the set X is not countable. It is an uncountable set. Maybe this is the simplest example of an uncountable set. The other example, because you told me to give you, the other example is a little bit different, but you have it in the lecture. It is related to the set of real numbers. So the interval 0, 1 is not countable. Consequently, so it's uncountable. Consequently, the set of real numbers is uncountable. What is the argument? The argument I gave you, it is the following. Again, by contradiction. Suppose that 0, 1 is equipotent with a set of natural numbers. That means its elements can be written as a sequence. So 0, 1 can be written as X1, X2, X3, and so on. Again, the contradiction will be obtained if we can define an element X which is in the interval 0, 1, and it cannot be X1, it cannot be X2, it cannot be none of these elements written here. In that case, the proof is over. And how we did that? We did that in the following way. We took the interval 0, 1, and we split it into 3 equal parts. Yes, here it's 1/3, here it's 2/3. Okay, and the assertion I make is the following. At least one of these 3 intervals, at least one of them, we shall take them as closed intervals. At least one of these closed intervals doesn't contain the number X1. Of course, for example, if X1 is here, these 2 intervals do not contain X1, so at least one. If, for example, X1 is here, then this one it contains, this one contains, but this one doesn't. This explains why I take 3 intervals and not 2. Okay, so at least one of these intervals doesn't contain X1. Let A1, B1 be that interval which doesn't contain X1. For example, let's suppose that this is it. This is our interval. This is this one. Yes, this is the interval which doesn't contain X1. And now we continue in the same way with this interval. We split this interval into 3 equal parts. And the assertion is that at least one of these 3 intervals doesn't contain x2 for the same reason as before. So let A2 be 2 be that interval which doesn't contain x2. On our picture, suppose that this is the interval. We continue. We split this interval into 3 equal parts. At least one of them doesn't contain x3. Let A3 be 3 be that interval which doesn't contain x3, and so on, and so on. So in this way, we get intervals like this, A1, B1, which contains A2, B2. Attention, yes, because you see A1, B1 is this one, and A2, B2, it was this one, smaller and smaller, which contains A3, B3. And so on, infinitely many. Yes, here we have an IN, AN, BN, and so on. So we have infinitely many intervals closed, and each one is included in the previous intervals. And x1 is not here, x2 is not here, x3 is not here, and so on. Yes? Now, these intervals are so-called nested intervals. This is how the term closed and nested intervals. In Romanian, it said closed and included. This means nested, included intervals. If you want a picture, it will look like this. This is the largest. Inside it, there is another one, there is another one, and so on, like a nest in English. So closed and included intervals, or nested intervals. And we have a lemma, which says that, a theorem, which says, we call it lemma, that if you have such intervals, then their intersection, the intersection of all these intervals, is not empty. It does contain at least one real number. So let Xi be that number which is in the intersection. So attention, that means that Xi belongs to all these intervals. That this means to be in the intersection. It is in all of them for every n. So Xi is in A1, B1, Xi is in A2, B2, Xi is in A2, B2, and so on. It is in all of them because it is in the intersection. It's a real number which is in this intersection. Conclusion, Xi, because of that, because Xi is in the interval A1, B1, it cannot be Xi1, X1, because remember, X1 was not in A1, B1. Because Xi is in A2, B2, it cannot be equal to X2, because X2, remember, was not in the interval A2, B2, and so on. So actually, this number, it's a real number, is different from X1, is different from X2. So this is the contradiction. We found a real number in 0, 1, which cannot be equal to X1, to X2, to nobody from here. So contradiction here, it is not the entire set 0, 1. At least somebody is missing. Who? This Xi. So this is an argument based on the so-called lemma of closed and nested intervals. This is how we call it at the lecture. So you have two different types of sets which are uncountable. The first example is based on Cantor's diagonal argument, and the second one is based on this property of the set of real numbers, that every interval is uncountable and is based on the lemma of nested and closed intervals. Okay. Other questions, please. Okay, if not, I recommend you to review if it is, or to relax a little bit before the partial exam, to review the basic notions. At the partial, you will have exercises which will be of the same type as you worked at the seminars and at the lecture. Make the union of both, yes? If you didn't work with countable and uncountable sets at the seminars, but I told you that I did it at the lecture, so you must know. So, but everything will be very close, if not identical, of what we work together at the seminar or at the lecture. Yes, please. Okay. If you not have other questions, I wish you good luck and see you tomorrow. And everybody at the, so tomorrow at 10 o'clock, only the two groups which have the partial tomorrow. The other groups should not come, yes? Okay.
Good night.
Good night.